Okay, so today we're doing the equilibrium constant. So this is the first part of the third inquiry question. Our syllabus outcome today is deduce the equilibrium expression in terms of KEQ for homogeneous reactions occurring in solution. So, firstly, there's some revision questions. Have a go at those. Once you're done, press play, and we'll go through the answers now. So, if an equilibrium system is disturbed, then the system will move to minimize the change. Again, that's the basics of Le Chatelier's principle. If a chemical is added, then the equilibrium will move away from that side. So if we add a product, it will move towards a reactants. If we add a reactant, it will move towards the products. If the pressure is increased, so when we increase the pressure, it wants to decrease it. So it moves to the side with fewer moles. And remember, that's always for gaseous reactions. If the temperature is increased, the equilibrium will move to the side that lowers the temperature. So again, if we heat it up, it wants to cool down, so it'll move towards the endothermic reaction. And all of those work both ways. Okay, so basically, if we take a product away, it'll move towards the products. If we decrease the pressure, it'll move towards the side with more moles. And if we decrease the temperature, it'll move to the side that's the exothermic way. So far, we've really only looked at equilibrium qualitatively. However, we can describe equilibrium concentrations quantitatively as well by using the equilibrium constant. Now, that's pretty much what this whole inquiry question is going to be about, is the equilibrium constant. Now, what is it? Well, it's basically a number that represents the concentration of reagents at equilibrium. Okay, so where does the equilibrium lie? Is it mostly products? Is it mostly reactants? Is it equal? Is there 10,000 times as many products as reactants or whatever? Okay, it's just a number that describes that. Now, as for what the numbers mean, we'll get to that in a future lesson. But what we're going to be doing today is looking at how to construct what we call the K expression or the K equation, which is how we actually determine the equilibrium constant. So, for an equilibrium reaction with A moles of molecule A plus B moles of molecule B plus blah, 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 which is in equilibrium with C moles of compound C and D moles of compound D. So our capital A, B, C, and D are our reagents. The little a, B, C, and D are our stoichiometric ratios. Okay. Now for that reaction, what our K expression looks like is this. So KEQ is the concentration of molecule C to the power of the stoichiometric ratio C, concentration of D to the power of the stoichiometric D, over concentration of A to the stoichiometric number of A, and compound B, concentration of B to the stoichiometric ratio of compound B. Okay, it all seems rather complex at this point, but we'll go through a few examples and I'll show you exactly what we mean by it. Basically, let's have a look at this equation. So we have our nitrogen dioxide in equilibrium with dinitrogen tetroxide. So this is the one we did in the experiment where we collected the orange gas in the syringe and compressed it so that it moved towards the N2O4 side, etc. So what we do, we take the concentration of the products, okay, so N2O4, and we put it over the concentration of the reactants, which in this case is our nitrogen dioxide. And then because nitrogen dioxide has a stoichiometric ratio of 2, we're going to put it to the power of 2. Okay, so you kind of see how we're constructing that. So we had concentration of the products over the concentration of the reactants, and each of them is raised to the power of the stoichiometric ratio. So N2O4 is 1, so it's a power of 1, but we don't have to write it. And NO2 is 2, so we square it. Okay. Let's have a look at this one. So this is our good old Haber process. We have nitrogen plus 3 hydrogens in equilibrium with 2 NH3s. So you see, we put the products at the top, so products there. Okay, so that's our products, and remember it's the concentration of the products, that's why we use the square brackets, and it's raised to the power of 2. We put it over the concentration of the reactants, so N2, that has a stoichiometric ratio of 1, so it's just the power of 1, and the other reactant is hydrogen, and it's a stoichiometric power of 3. Okay. Now, one big mistake made during the formation of K equations, and don't worry, we will do some more examples, is that students not putting the chemicals on the correct side of the fraction. So they might put reactants over products. Okay, but we want to do products over reactants, and there's an easy mnemonic that I love to use to help with constructing our K equations, and that is pork. Okay, so P-O-R-K. What does it mean? Now, just taking that image of the nice juicy pork and embed it into your mind so that whenever you think of K equations, you're thinking of that nice juicy roast pork. Okay, what does it mean? Products over reactants equals K. Okay, so this is our mnemonic to remember it. Products over reactants equals K. I'm going to be using that quite a bit. I still use it occasionally when I'm trying to remember which way to put them. So I find it really useful. So products over reactants. So again, if we have products, we're going to put the concentration of the products at the top. Reactants, concentration of the reactants goes at the bottom. Again, so this is the examples that we did. So we notice how we've got the products here, over reactants there. Okay, I think I've actually put that in as an animation, so I shouldn't have actually drawn over it. Same here, so we have the products over the reactants, just like that. So what are we going to do? Let's do a practice one. So here we've got chlorine plus carbon monoxide is a CoCl2. Now, we need to determine the K equation or the K expression for this reaction. So we're going to follow our mnemonic of products over reactants equals K. Okay. So products, we have CoCl2. So it's going to be at the top. So the concentration of CoCl2 will be at the top. CO will be at the bottom. Cl2 will be at the bottom. Now, we also have to have a think. What are the stoichiometric ratios? Well, it's 1 to 1 to 1. So they're all going to be to the power of 1. And so that's what our KQ expression is going to look like. Okay. So concentration of CoCl2 at the top over the concentration of chlorine times the concentration of carbon monoxide. Another example, oxygen plus nitrogen gives us 2 nitrogen oxide. Again, it's products over reactants equals K. So we're going to do the products at the top. So our product is NO over the reactants. So nitrogen, concentration of nitrogen times the concentration of oxygen. Now, having a look at the stoichiometric ratios, 1 to 1 to 2. Okay, so what do we have to do with the 2? Well, we have to raise the concentration of NO to the power of 2. So it ends up looking like this. So the concentration of NO squared over the concentration of nitrogen times the concentration of oxygen. Okay. Here, oxygen plus hydrogen is in equilibrium with water. Okay, so our products in this case are going to be water. Our reactants are going to be hydrogen and oxygen. So it'll be concentration of water over the concentration of hydrogen times the concentration of oxygen. Then we also have to think of the stoichiometric ratios, 1 to 2 to 2. So oxygen is going to be to the power of 1. Hydrogen is going to be squared. Water is also going to be squared. So it's going to look like this. Okay. Now, when we have a reaction, not everything's included in the equilibrium constant. The only things that are included in the numerical value is something that can vary in concentration. Okay, if the concentration of it can't vary in the chemical system, then it's not included in the K equation. And so what do we mean by that? So if you think of aqueous substances, so salts dissolved in liquid, you can vary their concentrations by adding more of that stuff. Okay, it'll dissolve, the concentration will increase. In gaseous systems, gases can also vary their concentration. So realistically, if we increase the pressure, that changes the concentration. So gases are also included in the K equation. Things that aren't included are pure liquids and solids that cannot change in their concentration. So for example, if we are doing a reaction that involves water, but we're doing it in the solvent water, we're not going to include the water in our K equation because the concentration of that doesn't really change because it's mostly water. Okay. Solids also aren't included because whenever a reaction is involved with the solid, it's always surface chemistry, so it doesn't really change the equilibrium. So we can add more solid, it's not going to change where our equilibrium lies. And so what we do is we exclude those values from our K equations. So having a look at an example. So for the equation lead chloride solid in equilibrium with lead 2 plus ions aqueous plus 2 Cl minus aqueous. Again, it's going to be products over reactants. So our products, Cl minus, so we need the concentration of chloride ions times the concentration of lead ions. And it's going to be over our reactants. But in this case, our reactant's PbCl2, and it's a solid. So solids aren't actually included in our K equation. So what we're going to do is whenever we have a solid like that, or one of the other things that is kind of not included in our K equations, what we're going to do is we're just going to replace it with a 1. Okay, so effectively what we get, the KEQ, or so the K equation or K expression for this reaction is going to be that. So it's going to be lead ions, so concentration of lead ions times the concentration of chloride ions squared, because again we've got that 2 in front of the Cl minus, and we're just going to put it over 1. Again, so wherever we have a solid or something else that's not supposed to be in the reaction, we're just going to put a 1, just because it doesn't vary. And so the KEQ for this equation is just lead 2 plus times Cl minus squared. Okay. Another example. So I forgot the animation on this page, so let's just imagine you can't see the bottom for now. Look at the top one. We've got chromate plus H plus in equilibrium with dichromate and water. Now this is one of the reactions we did recently. It was the yellow-orange one where we get the chromate's a nice light yellow. When we add acid to it, it forms a dichromate, which was that nice deep orange color. Now, doing the K expression or the K equation, we do products over reactants. So our products are going to be dichromate, so the Cr2O7 2 minus, over CrO4 2 minus times H plus. Having a look at the stoichiometric ratios, dichromate is 1, so it's going to be the power of 1. H plus is to the power of 2, so it's going to be 2. And chromate is to the power, has a ratio of 2, so it's also going to be squared. But you'll notice that our water is a liquid in this case. And because the reaction is done in water, it's not actually going to affect the equilibrium. So we're just going to cross that one out, and we're just going to put it in the reaction as a 1, sorry, in the K equation as a 1, and so it just ends up being that for our K equation. Okay. So here's another one. So determine the K equation for the following reaction. So we've got H2O gas plus solid carbon gives us H2 gas plus CO gas. So for our K equation, products over reactants, so we're going to get the concentration of carbon monoxide times the concentration of hydrogen over the concentration of water. Now, if we have a look carefully at this one, so carbon is a solid, so that's not going to be included. But the rest of the things are acting as gases. Okay, so it's a gaseous reaction, in which case we actually have to include the water because it's a gas. So it's not a liquid. So we're not doing the reaction in water. We're doing the reaction in a gas form. And so that's one of those things where it's not, we don't just cut out water, we cut out liquid water. Okay. So if it's as a gas in a gaseous reaction, we keep it in. So we need those three compounds in our K equation. So it'll be concentration, so products over reactants equals K. So products are carbon monoxide times hydrogen over water. All the stoichiometric ratios are 1, so they're just going to be the power of 1, like that. Okay. Let's have a look at this one. Determine the K equation for the following reaction. So calcium carbonate solid is in equilibrium with calcium oxide solid plus oxygen gas. Well, which ones are included? So gas, that's included. Solid, not included. Solid, not included. So what's our K equation going to be? Well, this one's a nice easy one. It's just going to be the concentration of oxygen. Okay. Again, we replace the other two with ones and we just get that. So concentration of oxygen. So nice, easy K equation. Another one here we've got hydrogen sulfate minus plus water is in equilibrium with H3O plus SO4 2 minus. Okay. So what's included? Well, first one's aqueous, so we include that. Second one's a liquid, so we don't include that. We then have H3O plus aqueous, which is included, and sulfate 2 minus, which is also included. So it gives us this K equation. So H3O plus times sulfate over the concentration of the hydrogen sulfate. So in summary, so the equilibrium constant's a number that describes where the concentrations of reagents at equilibrium lies. We'll get to actually using that next lesson. For the equilibrium reaction, AA plus BB plus blah, blah, blah is in equilibrium with CC plus DD plus whatever. The equilibrium constant's given by that. So concentration of C to the power of the stoichiometric ratio of C times concentration of D to the power of the stoichiometric ratio of D, so on and so forth. And the easiest way to remember which way to put it around is POR. Products over reactants equals K. Okay. So once you've got all that down, please go on to doing the questions. There's a lot of questions that just involve having you make the K equation for this, for the reaction. Be very careful of what you include. So remember, we include aqueous things in an aqueous equilibrium. We include gaseous things in a gaseous equilibrium. We always get rid of solids and we get rid of liquids, okay, because they're not going to take part. The other thing that you'll have to remember for these things is to balance the equation. So there's some in there that you need to balance, okay? If you need to balance, go back to the balancing equations lesson in module 1, just refresh yourself. There's plenty of exercises there to refresh yourself on that, okay? And that is all. Oh, yeah, sorry, there's a bit more summary. I mentioned those just a minute ago. So only things that with variable concentrations are included, aqueous or gas are included, and solids and pure liquids are not included. Okay, so please get onto those exercises, and yeah, that's all for today.